All right, good morning. Today we're going to talk about Math 111, Section 7.3, entitled Simplifying Radical Expressions. All right, take a look back in 7.1. Basically, we covered the foundations, defined and manipulated some simple radical expressions, talked about roots and what it means to be taking a root, etc. 7.2, we expanded on that to define rational exponents. Remember, that's just a fancy word for a fractional exponent. In other words, exponents that are fractions. And recall we did this material in a face-to-face class. But I am going to include questions on 7.2 in the 7.3 online exam. Let me write that down. Questions on 7.2 rational exponents will be included in the 7.3 online exam. Okay? All right, so be aware of that. All right, let's go on then and talk about simplifying radical expressions. Well, I guess you could say that we've already simplified some radical expressions. Well, the square root of 100, of course, can be simplified as 10. Well, that makes it easy because 10 is a perfect square, so the square root of 100 is going to be 10. You get a whole number out of this root when the radicand is itself a perfect square. How about something like this? The square root of 12. Well, 12 is not a perfect square. Well, what can we do here? Can we do anything to simplify it? I suppose we could always get a decimal approximation here, but I'm not getting at that. What I want to talk about is some manipulation like this. The square root of 12, well, 12 is not a perfect square, but embedded in 12 is a factor of 4 that is a perfect square. And I can rewrite then this root expression in this way. I can say 12 under the root sign is 4 times 3. Now, you may have already guessed we can break up a root sign or distribute a root sign over factors of a product. The square root of 4 is 2, and I can rewrite this original expression as 2 times the square root of 3, or what some might call 2 root 3. And I call this answer simplified radical form. And all that means is you've taken out all that you can from under the root sign according to this process. Now we can do this with square roots, cube roots, etc. Let's do some more examples with square roots before we move on to the higher index roots. How about if I ask you to simplify the square root of 98? Well, 98 is not a perfect square. I suppose we have to ask ourselves, what is the greatest number that's a factor of 98? In other words, what is the biggest perfect square that's a factor of 98? I think we can all see that 49 is buried in 98, and 49 is a perfect square. All right, I can then break up this root as the square root of 49 times the square root of 2, and of course that reduces to 7 times the square root of 2. So the square root of 98 simplifies as 7 root 2, and again this is what we call simplified radical form, or sometimes called simplified root form, depending on whether you like the word radical or root better. Alright, now we've done a couple examples with square roots or second roots. What about third roots or cube roots. We can play this game with cube roots as well. The cube root of 54, for example, if I ask us to simplify this expression. Well, 54, let's see, I'm going to be looking for perfect third powers or perfect cubed powers here. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, so I'm pretty confident here. I've already gone up to 64 here, and 54 does not appear on this list. So 54 is not a perfect third power, but 27 is a factor of 54, or I can view it as a factor of 54, and 27 is a factor of 54. So I can break this up as the cube root of 27 times 2. 54 is 27 times 2, is it not? Alright, so I can then break up a root over a product of factors, and I know that the third root of 27 is 3 because 27 is a perfect cube, and I would have as a final answer 3 times the third root of 2, or 3 times the cube root of 2. So this original expression equals this in simplified root form. Okay? Alright, not so tough if we practice it a bunch of times. Let's try something. Alright, we've got a fourth root here. I think this one's right out of the textbook. Alright, what I'm going to claim here is that anything that's a perfect fourth power, that's a factor of 48, I can pull out from under that root sign, similar to my previous 2 or 3 examples. Alright, so I'm going to be looking for perfect fourth powers here, buried under that root sign. 1 to the fourth is 1. 2 to the fourth is 16. What's 3 to the fourth power? It's 81. Is it not? Way too big. So what I'm guessing here is, well, 48 is not going to be on this list, but 16, I can see 16 as a factor of 48 under the root sign. Can we not? Let me rewrite this expression then as minus fourth root of 16 times 3. Alright, I can break up that root sign over that product. So I claim this is equivalent to negative fourth root of 16 times fourth root of 3. Well, the fourth root of 16 we know is 2, because 2 to the fourth power is 16. So outside the root sign, now I get minus 2 times the fourth root of 3. So there would be my simplified, most simplified response. This is equal to this in simplified root form. Okay. Let's try something a little nastier here. The fifth root of 128. If I ask you to simplify the above radical expression. Well, I'm going to be looking for perfect fifth powers that I can take out from under that root sign. Let me make a list of perfect fifth powers. 1 to the fifth is 1. 1 to any power is 1. 2 to the fifth power is 32. 3 to the fifth power, what's that, 243? Way too big, so 128 is not going to be on this list. But I see 32, and I think I can envision 32 as being a factor of 128. Let's see. 128 is 32 times 4, is it not? I believe it is. 4 times 30 is 120, and 4 times 2 is 8. Yes, it is. And, of course, 32 is a perfect fifth power. It's on my list right here. So I can break up that root sign over that product of factors. It's a 4 under that root sign there. And the fifth root of 32 is 2 times the fifth root of 4. All right, 4 has got to stay inside. You're completely simplified when you can't pull anything else out from under that root sign. So here's my final response in simplified root form. Alright, so we've done square roots, third roots, fourth roots, and fifth roots, simplifying numerical radicands. What about when we've got variable expressions? Let me get a fresh screen here. Oops. How about simplifying radical expressions with variables, not just numerical values under the root sign? Alright, how about something like this? Classic example here. The square root of m to the ninth. Well, I can take out as many powers of m that are multiples of my index. Now, of course, when no index is specified, we assume an index of 2. Right? We assume square root. Well, m to the ninth is not going to be a perfect square, but m to the 8th power is. So what I can do is rewrite m to the ninth under that root sign as m to the 8th times m, and I can then break up that square root sign over that product. Alright, now both of these factors are really 7.1 type problems. What's the square root of m to the 8th? Well, I claim that's m to the 4th power, because m to the 4th squared is m to the 8th, times, well, the square root of m. I can't simplify that any further. I just write that as the square root of m. Alright, so I can specify an index of 2 if I like. Under that remaining root sign, I think most of us would probably say m to the 4th times the square root of m. Alright, I just want to highlight something. You're done when you can't take anything out from under that root sign. In other words, when the power on any variable that might be in your radicand is less than your index. And 1 is less than 2 here, so that m has got to stay inside. Here's my final answer. Let's try another one. Do another square root here. We'll be doing some higher index roots in a minute. The square root of 128 a to the 5th power. Well, again, my index is 2 here, so I'm going to be looking for perfect squares, perfect powers of 2 that I can take out from under that root sign. Let's consider 128. I'm looking for perfect squares. 1 squared is 1. 2 squared is 9. 2 squared is 4. Hang on a minute. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. 10 squared is 100. 11 squared is 121, and 12 squared is, of course, 144. Alright, the idea trying to get across is 128 is not on this list. We've gotten up to 12 squared is 144. We're already too big. So 128 is not a perfect square. But I think you'll agree it contains a factor of 64 that is a perfect square. 128 is 2 times 64. So I can rewrite this root expression. Remember, no index specified means an index of 2. I can rewrite 128 as 64 times 2. Alright, now what I'm going to do is I'm going to pile up the factors that are going to come out from under the root sign on the left. Similarly, a to the fifth is not a perfect second power, but a to the fourth is, and I can rewrite a to the fifth as a to the fourth times a. So the perfect square factors that are embedded, I can separate off to the left. What I call the residue factors, the stuff that's going to stay under the root sign, I'll push off to the right. The square root of 64 is then 8. The square root of a to the fourth is a squared, and the square root of 2a is just the square root of 2a. I can't take anything else out from under that root sign, so I call that simplified radical form. Let's try some third roots, trying this with third roots as well. Now don't panic, remember it's okay to have a negative radicand when your index is even. So we're going to play this game with a third root now. Well, if I look for perfect third powers, well, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, and regarding this coefficient here, we're already too big, so 24 is not on this list, right? But I think you can agree, minus 24 contains a factor of 8, and 8 is on this list. So what I'm going to do is break up that radicand. I'm going to say minus 24 is minus 8 times 3. Everybody agree with that? And similarly, x to the fifth power, well, 3 factors of x I can take out, 3 powers of x I can take out, and that means 2 factors of x have to stay inside. Alright, I can then break up that root sign over these factors. Now I'll worry about this left-hand expression first. The cube root of minus 8 is negative 2, of course. The cube root of x cubed, that's just x, times what? Times the cube root of 3x squared. Alright, so I've simplified as much as I can. I've taken out everything out from under that root sign that I can, and there is my final answer. Minus 2x times the third root of x squared. I'm going to do one more today, and this is in the upper reaches of the homework assignment. Alright, I'm going to ask us to simplify the above radical expression. In other words, express your answer in simplified radical form. Alright, again, I'm going to basically pile up perfect fifth powers under this root sign on the left edge, and then break up the root sign as I've done in my previous 5 or 6 examples. A to the ninth is not a perfect fifth power, but a to the fifth is, so I can say 5 factors of a are going to come out, and that means 4 factors of a have to stay inside. Similarly, b to the seventh is not a perfect fifth power, but b to the fifth is, so b to the fifth can come out, which leaves me with 2 factors of b inside, or a b squared inside. And c to the fifth power, well, c to the fifth power is a perfect fifth power, of course. So what I'll do now is break up that root sign over the perfect fifth powers and the non-perfect fifth powers. Of course, I can just mow these down now. The fifth root of a to the fifth is a. The fifth root of b to the fifth is b. The fifth root of c to the fifth is c. Times the fifth root of a to the fourth, b squared. Again, you're in simplified radical form when there are no factors under the root sign that have an exponent greater than your index. In other words, all your exponents under the root sign are less than your index. So I call this simplified radical form for your original expression. Oh, let's do one more. This is another fifth power, or fifth root, I should say. This is This is number 102 in your homework list. Another fifth root. I suppose if you can handle fifth roots nicely, you can handle any root, any index root. Look at the fifth root of 243 times r to the 22nd power. And let's see, I think I recognize something. 3 to the fifth power is 243. Watch as I make a list. Of perfect fifth powers. 3 to the fifth power, that's 3 times 3 times 3 times 3 times 3. 3 cubed is 27, times 3 is 81, times 3 is 243. Alright, that's nice. So that means this whole coefficient is going to come out. No residue from the coefficient. How many factors of 22 can come out? Well, again, you can take out as many powers of your variable that are multiples of your index 5. So what I'm going to do, I'm going to rewrite that radicand. 243, all of that's coming out. I think 20 powers of r can come out because 20 is a multiple of 5. And that means 2 powers of r, or an r squared, is going to have to stay behind. Alright, the fifth root of 243 is 3. The fifth root of r to the 20th power is r to the 4th. Because r to the 4th raised to the 5th power gives me r to the 20th. Times the fifth root of whatever is left inside the fifth root of r squared. Alright, so there's my final answer there in simplified root form. And I think we're reaching the 24-minute point, so we'll call it a day. And again, please be sure to know that 7.2 questions, rational exponents, will be included in the 7.3 online exam. Okay? Alright, so this concludes section 7.3, simplifying radical expressions.